This is the first recording of a series of remote lectures that essentially are designed for engineers that are taking second year course Geology 2017. The idea of this course is really to introduce some basic earth science concepts that will be handy to a broad variety of engineers. But yes, it's mostly a course that deals with the classification of rocks and provides a general understanding of geomaterials. So let's review some of the key objectives of this course. The first really objective for the course is to provide an illustration of fundamental earth science concepts. We can make a very quick example of that if we think in terms of plate tectonics, for example. So our planet has processes that operate at a variety of scales, and these processes often are dynamics, and this dynamics leads to the formation of different rocks. So what we will try to achieve with this course is to find a connection between the multi-scale processes that occur on our planet and the type of outcomes we get, which are different rock types. So we will study different earth tectonic environment as part of this, and then also study different classification methods so that we are able then to classify the rocks. Quite commonly, this type of classification takes place using physical analysis. So you take a specimen and you use a number of tools to recognize either the mineral or the rock you are examining. So in this case we have some examples of the tools that geologists will commonly use, and these are used to test for hardness, and you have here the copper coin as a good example, or the knife, which usually are material with different hardness. We can test for magnetic properties and also test for particular types of chemistry using hydrochloric acid, like here, and also we can magnify a specimen to understand better its structure. This course considers a number of extra materials which are provided through a cloud support, essentially. So we place on the cloud a number of documents, and this will be available through a link that I will provide, and also the D12 portal. I think it's recommended that you print out some of these things for your sake, for your own sake, and sort of look at this, especially with respect to the lab applications, really. In terms of marking and examination, we have essentially three major components: 2 lab tests and a structural assignment and a final exam. For the online course, there is no structural assignment, and participation is usually assignment based. So each series of lecture will have some assignments that will support your learning and sort of provide a way of checking how you are progressing with the course content. The course is subdivided in mostly 3 weeks segments, with some exceptions. But yeah, the big chunks of the course really have 3 weeks segments. The first one is the one on igneous rocks. It looks at classifying igneous rocks, identifying them, and also look at the environments of formation of these different rock types and all the associated tectonic processes. So one example are, for example, volcanoes. So we look at the formation of volcanoes, how the volcanoes contribute to the production of particular types of rocks. Weeks 4 and 6 are instead dedicated to sedimentary rocks. We're going to use this segment of the course to explore sedimentary environments and different sedimentary rock types that are the result of different processes occurring in these sedimentary environments. For example, fluvial versus marine environments will have different types of sedimentary rocks. Some time will be spent also towards the understanding of carbonate rocks and those even more unique environment of formation. And so there will be an introduction to depositional environments for these rocks. Week 7 is all about the metamorphic world. We will learn that metamorphic rocks are the result of a transformation of pre-existing rock types. So igneous and sedimentary rocks can be transformed usually for increases or decreases in pressure and temperature. We tend to convert the mineralogy of a rock into something else, and so we form a metamorphic rock. So we will give a definition of metamorphic rocks, review the key minerals that are found in metamorphic rocks, and also discuss a number of factors that drive these changes in mineralogy and sometimes in the composition of the rock, and also introduce other important concepts such as metamorphic phases and also different types of metamorphism depending on the tectonic environment of formation. Weeks 8 and 9 are dedicated to tectonic structures. So we will look at the concept of a fault, which is a crustal discontinuity, its classification, the identification of different geometries of faults. Essentially, the anatomy and evolution of fault zones will be investigated in the earlier part of this segment, and then we will look at the processes that leads to the formation of faults. For example, cataclasites, so the development of cataclasites, which are a particular type of tectonites found in these weak zones in the crust or area of weakness. In this context, we will look also at the role of fluids, slip indicators, and some other types of deformations. The final part of the course is related to Salisbury in a way, and in fact you see here the magmatic nickel copper PG, which is one of the groups of major mineral resources or georesources that we find here. So of course for a geologist that and an engineer that is involved with the mining, it is key to understand basic concepts that are around the formation of ore deposits. So remember, as an anticipation, an ore deposit is essentially a portion of the earth crust that have anomalous concentration of a key commodity. Okay, by anomalous we mean concentrations that have an economic value and that they are exploited for a purpose. For example, let's say we mine a lot of copper here. Usually copper is used in electrical engineering quite a bit, So it is important to understand how you recover copper, what kind of deposits are exploited for copper, and yeah, magmatic nickel copper PGE deposits are one of them. Okay, so understanding what the different types of deposits offer to a geologist and an engineer is key to then understand also a number of issues that are around the exploitations of mineral deposits. So this brings you, to the first really ideas of engineering geology. So in this course we focus on engineering geology, but we tend to sort of look more at the geological side of things. So why an engineer needs an understanding of earth science. I think there are a number of bullets here that highlight that you need to be able to analyze a geological process and understand it. So let's say we are deforming some rocks with a fault zone, so a discontinuity, a fault is commonly a discontinuity in the crust. So a mechanical discontinuity, the engineer needs to recognize the discontinuity, understand how it moves, so that you can do your stability evaluation. Understanding of principal type of rocks will be helpful because they have different geomechanical properties. Also, you have to understand how different geological conditions influence the engineering activity. So we could make an example. A geological condition could be a variety of clays. So many times when you construct a foundation, you will need to investigate the different type of clays that are present, and this is because water can over time can influence the behavior of a clay material, and so it can change completely the type of foundation that you have to build to ensure stability of a construction. And finally, an appreciation of the richness of underground resources is what I was already mentioning. So an engineer, especially that works in the mines, will need to know what are the different type of deposits and some of the key characteristics of the deposits. So definition of engineering geology. This is really a brief statement, but you have to have a keyword in mind, which is interaction. So engineering geology is a discipline that looks at the effect of interactions of any working that an engineers develop. So for example, let's build a bridge. We need to perform a proper analysis of pillars on a bridge and their interaction with the support, which is the land that is underneath the pillar. And finally, prevention. So we need prevention and remediation of geological hazards. We will see some of these areas in a later discussion, and I guess this can be summarized really from the definition in sort of a certain number of studies that engineering geology has to go through. So we need to define the geomorphology, structure, stratigraphy, lithology, and groundwater conditions. So water is so important in this type of problems because it's a dynamic factor. So the ingress of water can change completely the geotechnical behavior of a phase, for example, in a mine, and increase instabilities. So these are things that needs to be documented and understood. So assessments of mechanical and hydrologic behavior are important, both for the soils or unconsolidated materials and rock masses, and also the prediction of changes of these properties over time is the critical aspect here, really. So if we examine more in detail the intersection of engineering with earth science, we have essentially four distinct fields. So we have the project construction field, which I already mentioned. So any kind of foundation for buildings is part of this group. And so here is mostly stability analysis that is conducted. Natural hazards are the other key aspect. If we think slope analysis is part of that too. So if you have, failure of a soil, quite often leads to a significant movement of land mass, and these can represent significant natural hazards, which are often linked to processes such as earthquakes. Okay, so earthquakes, volcanism needs to be understood by an engineer and needs to be mitigated. The key aspect here is the heterogeneity of these processes. They are often localized in specific areas that are particularly weak in the crust, and as a consequence of that, often mapping the geospatial distribution of these processes is quite helpful to mitigate the risk related to natural hazards. Geological resources, we have mentioned that already. Here we tend to reiterate quite a bit in these discussions, but it's to sort of make these concepts resonate in your mind. So raw and processed geomaterials are mined for their industrial application mostly. Environmental pollution is the last one, really. Some environmental engineers and geologists will conduct geochemical surveys. So an engineer needs to know what a geochemical survey is and sort of figure out its value. So understanding environmental pollution, which is the distribution of anomalous concentrations of chemical elements that are an harm for the environment, is certainly one of the things that it's important to understand. So this discussion now considers a number of sort of quick examples of the different sort of field of interaction between engineering and geology. So if you remember, I mentioned project construction, and I was talking about pillars, and here you have three different types of pillars. And so we have that these pillars are sort of placed within some land, and this terrain has different geomechanical characteristics. So in case A, it's using essentially a simple pillar because the unit of rocks that is supporting the base of the pillar is represented dominantly by limestone, and it's essentially a stable overburden. And so we have, a stable overburden on top and a stable base represented by limestone. So this is a quite favorable situation for a simple pillar. But if you have that the overburden is dominating, like in the second case, of course you will have some problems of stability, because an overburden is quite often less cohesive, and as a consequence of that it's supporting less the pillar. So how do you avoid a deepening of the position of the base of the pillar? Quite often you have to enlarge the footprint, and so you use an elephant foot-like base, and also you tend to reduce the weight of the pillar. And so we have hollow pillars, like the example here, that essentially have an internal cavity. Other example that is even more challenging is the cage pillar. Here, of course, we have a situation where the overburden is completely unstable because of a sloping issue. And so we have that at the base of the interface between the limestone and this overburden that is more argillaceous, you tend to have sort of that these will move because of its instability. So you need to protect your pillar, and so this is why you have caged pillars that act essentially as a support for the surrounding materials. Luckily, the basement here is represented by limestones again, and so you can ensure that the pillar is supported enough because of that. But still, because of this instability, and I think because of the momentums that are sort of involving rotation at the base, we tend to increase the foot size quite a bit. So remember, active sliding is a key issue. So understanding the interaction between pillars and surrounding geomaterials is critical. And here we see an example of a natural hazard that is linked to geology. In this particular case, this is an example of a landslide that has affected a road. So you can see all sort of disruptions on the surface of the road with a number of fractures that developed. So this is an indication that, of course, constant landslide monitoring is necessary, and an environmental engineer would have to be aware of areas that are at high risk for landslides, and so rely on geological reporting for that. So we have here an example of a geological map. We look at geological resources in this case, and you will find included in the package of lecture assignments an example that really is a problem of mining materials that is related to this map. I believe this area is in Switzerland, and it's looking essentially at different colors that represents different rocks, and these rocks happen to have a different chemical composition, and so often an engineer will need to build something using, for example, Portland cement, which has a specific composition. So you will need to know how to blend geomaterials to obtain the required composition, and so essentially this translates in mining differential volumes of rock units which are known to have specific chemical compositions again. So this introduction is now concluded, and you got sort of the picture of what environmental engineering in the last part of this talk, but in general, engineering geology is sort of a science that leads to understand really well the interaction of human construction and land, or human workings and land. So that's the key objective. From the side of geology, we need to really understand then a number of processes that leads to the formation of rocks, and these will help, with the understanding of all the aspects that are critical for the work of an engineer. So in a general sense, geology is a science that is very observational, as I said before, and it's really dealing with the physical structure and substance of this planet. We look also at a brief introduction of the history of geology in this initial lecture, because it's interesting to see that in light of the observational nature of this science. So the history of geology, it's I think educative to learn that the earliest scientists and philosophers, for example, Leonardo da Vinci was one of the first to realize that lithification or processes occurred and embedded organic compounds or biological systems or the remnants of biological systems. You can see here an example of Blue McKellas, which is essentially a rock that is dominated by fossilized marine shells. You can see the scale here of the sample is roughly 5 centimeters. And yeah, quite often to a process which is called lithification, we form sedimentary rocks that are essentially a bunch of shells that have been cemented all together. The problem is that some of these rocks are found on the top of a mountain range like Tibet, so on the Everest, for example, and this represents sort of a paradox, because we know these rocks and these organisms tend to form on the bottom of an ocean. And so if that's the case, then the question that really puzzled Leonardo at the time was how that could happen, and he envisaged some major sort of cataclysm or movement that would explain the uplifting of rocks that had these characteristics. By uplifting, I mean bringing them sort of at a higher level at surface and find them really at the top of a mountain is a good example of that. So you see, it's roughly in the 16th century that Leonardo thought the mountains are ancient shorelines that have been uplifted. It's a very interesting intuition, I think, considering the time. But earlier philosophers, like Aristotle, he could infer that these processes are cyclic, which is also quite important. So understanding that there is a continuity of geological processes that tend to repeat, it's quite critical, and this is linked to some of the sedimentary deposits. So the concept of stratification in rocks. So even earlier than that, I mean, we have the earliest recognition of fossils and even mythical sort of ideas about divine creation of Earth, which we know it's an accretionary planet, were sort of instrumental, I think, to build this idea that geology is a science that looks really at understanding the structure of our planet at different scales. But then historically we tend to have a transition from questioning of the tectonics into studies that are more interested in the formation of Earth as well as its evolution, and this culminates in what is called continental drift theory of Wegener. So another important concept in geology is this distinction between the sciences that study earth materials or geomaterials. One is mineralogy and the other is petrology. So here we give the first definition really of a mineral, and you can see minerals are the units or building blocks of which rocks are made of. Petrology is the science concerned with rocks, So we will do also some petrology to essentially describe and understand again the processes that are commonly used by geologists to classify the different rocks. The question of why mineralogy is useful to engineers, I think is almost self-explanatory given the premise of this lecture. So anytime you understand the mineralogy of a rock, you will be very accurate in evaluating the strength of the rock. And this again is critical, for example, to analyze some of the mechanical properties that are important for the development of a construction. So a better understanding of mineral distribution and its structure will help this type of analysis. We will see that rocks are quite heterogeneous and they have a variety of textures. So by textures, it is meant the organization or geospatial organization of minerals.
Okay, if we look at the main characteristics of minerals, just to revise some of the initial sort of overview of the definition of a mineral, we should say that usually a mineral again has a defined chemical composition. So you can take a carbonate, it's commonly composed of calcium that is bound to groups of CO3. So essentially carbon and oxygen atoms, and these are repeated in space. It's essentially like a template, and a mineral has essentially a well-defined ordered structure. There are of course exceptions to these concepts. For example, on the side of the chemical composition you will get substitutions that take place, and these can include usually a number of anions or cations that will replace in the structure for other elements. So for the carbonate, for example, it's quite common to have substitutions like in the dolomite, in which you have essentially that magnesium substitute for calcium. In terms of the structure, most of the minerals will be ordered, but there are a few exceptions. For example, volcanic glass, it's represented by what is called an amorphous mineral. An amorphous mineral usually have unordered structure, which make them particularly hard and strong. So that's essentially linked to the chemical bonds. And so if we will see that we have different chemical bonds in minerals, and some are ionic bonds, some are covalent bonds, and they usually have a major impact on the characteristic. So the geomechanical characteristics of the mineral will change depending on the structure that the mineral assumes. In most cases, minerals will be solid, although there are few exceptions. There is a cool example here in this image. If you look carefully, you can see some spherules of mercury, and yeah, mercury is very close to sublimation, so you can find it in nature at normal temperature in a liquid state. And so droplets can be found in specimens of this type that essentially come from a mine and represent ore from Almaden in Spain. Okay, so I was mentioning chemical bonds. Some examples of that are in this slide. We could talk about a ionic compound such as halite, so NaCl, so mostly a sodium chloride, and you can see straight away that this mineral, has a cubic organization of the different atoms, and in response to that you get fracturing along well-defined 90 degrees oriented planes. So you can see a staircase of fractures that essentially are commonly an indication of the cleavage of the mineral. Other example down here of a diamond, so a compound that is dominated by carbon, and you see mostly tetrahedrons in this case, or octahedrons more correctly. In this example you have an octahedron of diamond, and the diamond will change its configuration if it's usually transported to a lower pressure temperature condition. And so if you heat up at normal conditions on the surface of the earth, so 25 degrees and 1 atmosphere, and you take a diamond and you put it on a flame, what happens? And I could ask you the question, what do you think is going to happen? Is that you change the mineral structure. It essentially reorganizes itself, because what we say is that the mineral will be unstable in a different conditions of pressure temperature that are actually not the one where the mineral crystallized firstly. Okay, so if we move a diamond to surface, we heat it up, we'll get what is called graphite, and you have an example of graphite in here. A completely different structure here, more a series of hexagons and that form well-defined layers, and these layers are then particularly weak because they commonly are separated by van der Waals forces, and these will allow actually to scrape off easily with your nail. You can scrape off graphite. Instead, if you try to do it with a diamond, it will be much harder. In fact, if you think in terms of hardness, the diamond is actually the strongest material on the planet. Okay, so very different mechanical properties in relationship to temperature, pressure of formation of these different minerals, but minerals that have the same chemical composition. So they are all made up by carbon, but the organization, the structure of the mineral is so critical that it influences dramatically both the optical properties as well as other properties such as mechanical strength. So I think I've addressed that. If you look at the difference, it's also on how metals tend to exchange electrons. So quite often in a ionic case you have that there is a jump of an electron from a cation into the anion space. So you can see here the example. We take one electron from the outer shell of potassium, actually this is sodium, sorry. And so we take sodium and expel an electron, which is going to be part then of a Cl anion. And this leads to stability, it stabilizes the compound, but if you see the clouds of the distribution, it's well separated. So the two atoms have electrons that are well separated. A clear difference is visible here. So in a covalent case, the electrons are in common between the two atoms. So we have hydrogen in this example. And the result is that the structure is much more packed, so the atoms are closer to each other, and this is resulting in a stronger bond. so covalent bond is quite often stronger and will result in a much stronger material. So in the examples before, the diamond had this covalent bond. Okay, crystal structures can be often represented with cells of variable shape. Since this is a cubic compound, so as a cubic symmetry, we use a cubic cell. And again, this is a sodium chloride. So the idea is that you find essentially a cell that contains a certain number of atoms, and these are repeated in space infinitely. So in this image, the lines represent a symmetrical lattice that connects a number of nodes that are representative of the different atoms I was mentioning, so sodium and chlorine. And this forms essentially a three-dimensional structure. The smallest unit is defined as the volumetric unit cell, and it contains the minimum amount of atoms that are representative of this particular compound. So lattice has different properties, but one key property is the lattice is defined as the lattice density. This has important sort of outcomes. Usually the faces of a crystal tend to be the one that have the denser number of atoms, so the ones that have a higher level of lattice density, and this is a function of the angle that you consider while intersecting atoms within the unit cell. So you have an example here with 45, 33.41, and these are the angles. And so at different angles, you can count the number of atoms that you encounter. So in this case, we have 1, 2, 3, 4, 5, 6, 7. And in this other, we have 1, 2, 3, 4, 5, 6, 7. So very similar. But if we use this one here, we have 1, 2, and only 3. So the two faces that tend to develop are this case 1 and case 2. By face development is essentially the most peripheral part of a crystal, and it's how the crystal essentially grows. So a crystal will form either a cube or it can form other geometries, and we'll see some example later. So usually high density planes are more likely to form faces on a crystal during growth, or of course if you fracture the crystal, you are exposing those high density faces, which so the internal discontinuities develop along those high density surfaces, I would say. Well, so what are the criteria used to identify minerals? Symmetry, as you can imagine, is one critical aspect because of the fact that you repeat a unit cell in space. You tend to develop specific symmetries, and the way in which the unit is copied is quite important because we have different rules, and these will allow you to recognize the symmetry of different minerals. Physical and chemical properties, if you remember at the beginning of the lecture, I mentioned those tools for the identification of strength or hardness of a mineral, as well as optical properties and reactivity to acid, and also magnetic properties. So again, optical properties are also represented in here. So color, translucency, so the ability of the crystal or mineral to let the light go through it is important, and also how much of the light is bouncing back. In some cases, it will be completely reflected off the surface of a mineral, and so you will have a specific type of reflectivity that you need to recognize. So these are just some of the key criteria. Really, we could consider also density, for example. Density is quite important because it gives you straight away an indication of the major families that group or groups that represent minerals. Usually oxides are quite heavy if compared to silicates, for example. Symmetry elements, we commonly have within the unit cell, you will have repetitions that follow specific reflection planes. And you have some examples here of the different planes of symmetry that allow mirroring of the basic structure. In some other instances, you have a rotation taking place. So you have n-fold rotation axes of symmetry that are essentially starting from the center of the cell and can be normal to all the faces in this cubic example, or actually intersect the corner coordinates of the cell, as well as the middle points, or the edges of the cube. So the mid points. So if you rotate this cube along these axes of a specific angle, it will get in the same position. Okay, and that is an indication that these are axes of symmetry. Okay, in these other planes, the same amount of atoms that is on one side will be repeated on the other, so it's like a mirror effect. So we have planes, we have axes, and yeah, it depends. The number you have here indicates the number of possible rotation, so that you have a repetition. So on these corners is 3 times, here is 4 times, and these other, the edges are 2 times, meaning that you can rotate only of 180 degrees to get the symmetry to be respected, basically. So these have different symmetry order. Based on these characteristics, we can recognize 7 classes. Okay, so we have the triclinic, monoclinic, rhombic, cubic, which are some examples. If we look at that more in detail, usually the 7 systems of symmetry that are present in the most common minerals will tend to have specific rules, and these are dihedral angle rules, and also cell size rules. So if we start with the cubic, this is one of the most simple symmetries because it's essentially looking at a cell that have the same edges and also has the same angles. So all the angles between the faces of the cell will be 90 degrees. If you move into the tetragonal, you maintain the angle rule, but you have one edge that is longer than the other, so it's more an elongated cube. And you have some examples of the key minerals like zircon and rutile. So this is an oxide of titanium, and zircon is another oxide of zirconium, and they all have these elongated crystals and 90 degrees angles. So that's a classical shape of one of these crystals. In the cubic, I forgot to mention, the halite example we mentioned before, but in some cases you might develop again dense faces at 45 degrees, and so you might get examples of B pyramids like this with fluorite, or dodecahedrons like garnet and pyrite as well. So very more complicated multi-phase geometries may develop. Again, with these other groups, slightly different, and you get the more complex cases in which all the faces are different, basically, because you have different angles and different lengths of the edges of the cell. Okay, so that's how you classify minerals. So it's important to understand that specific minerals will belong to one of these 7 groups, and this is quite useful, especially this first one. If you can identify a cube or an octahedron like this, well, quite often you can then identify the mineral, because you know that it's a cubic mineral. So when you have recognized the system, you're then able to relate to some specific minerals that could have that geometry. Another example here, we look at a cubic mineral. I was mentioning it before. As soon as you start to see a geometry like this, so a polygonal shape that is essentially a combination of octahedron and cubic, and you can see the different phases of development of the faces while the crystal grows. So you start, with the basic shape that is mostly octagonal, I would say, and progressively reduce some of the faces that are orthogonal to the diagonals here, and these will decrease in dimension until they disappear, and you end up with a cubic crystal in the final phase of growth. Of course, sometimes the mineral stops his growth because some of the chemical condition or physical condition will stop his crystallization or his ability to crystallize, and you end up with hybrid geometries like this example here of likely a pyrope variety of garnet. So interesting, again, to keep in mind that the geometry can be quite complex, but still you can see that this is fairly well-rounded mineral, and that's a good indication that it's a cubic mineral. And in the particular case, it's a garnet. Sometimes minerals will grow along well-defined planes of symmetry, and these are termed twinning. So you have here a clear plane of symmetry that is influencing the growth of this crystal of quartz. Another example here of cruciform twinning, which is quite common in a metamorphic mineral called staurolite. So you get essentially that you can draw a plane here and you get the same symmetry on both sides. So these are, in this example, Japanese twinning is kind of a typical feature of quartz. So when you see it, you can determine that this is a quartz crystal more easily. Of course, you get also these bipyramids, and the crystals are quite elongated, and they will be very hard, and they do not show any clear cleavage, and so that's another good set of indicators who will help you with the recognition of quartz. Quartz is pure silica, but crystallized in the trigonal system or tetragonal system, I think it is. But yeah, twinning can help you with the identification of minerals. That's certainly one key aspect, and that works really well also with staurolite or other metamorphic minerals. We'll see them when we talk about metamorphic rocks. If we move into the physical properties, we can relate minerals to a scale, Remember that you can scratch minerals against one another, and so you will be able to understand if you remove by scratching a particular mineral, if you are able to remove part of his face, that will indicate that the mineral is softer than the one you used to scratch it. So that's the basic idea. In addition to the minerals themselves, you can scratch them with your fingernail, a coin, a pin nail, a glass, and so on. So the tools I've sort of discussed much earlier in this lecture. And so this can be lined up into a scale, which is termed the Moss hardness scale. So very sort of dated concept, but still quite useful today for the identification of minerals. So remember that the softer mineral is talc and the hardest is diamond, and in the middle you have a number of other minerals that we will learn to recognize in this course. So you have also other sort of summary in here with more information about other things such as a steel file or a strict plate and quartz itself. So much harder minerals can be also used for scratching, and the steel file also is quite hard and could be useful to recognize the hardest mineral if you have them. We don't have diamond, unfortunately, in this course, but it's good to keep in mind that is at the top of the Moss scale. Fracture and cleavage, these are key properties for the recognition of some of the silicates, so things like muscovites, mica, and also amphibole and pyroxene and calcite will have a characteristic number of cleavages. So if we start with quartz, we have no cleavage, and quite often quartz will break, forming uneven fractures that are fractures that have a conchoidal surface, so a curved surface. Instead, if the surfaces of breakage are quite flat and you have a single cleavage, quite often this leads to minerals such as micas, because they have a preferential plane of weakness very much similar to graphite. So the carbon we were talking about earlier with those van der Waals bonds. Two cleavages are characteristics of amphibole and pyroxene and the way they intersect themselves. And you can see an example on this sketch. It's quite important. So amphibole will have 124 and 56 degrees, so you have uneven angles between the intersections of these cleavages. So they look like a set of planes or parallel fractures that influence the entire crystal basically. And these are quite important, especially if you have a hand lens. You will be able, if you look carefully, to identify some of these cleavages, which will help you with the distinction between a pyroxene and an amphibole, which unfortunately are very similar in color. So they're all black, and often they're difficult to differentiate in a rock. Okay, if you find three cleavages instead, you either are in a situation in which you have a feldspar or calcite, like this example in here, which is, to give you a quick indication, you have to look at multiple faces, not just one. And if you can see high angles between multiple sets of multiple faces, then it's likely that you are working with a mineral that has effectively three planes of cleavage. How do you know that? You have one plane oriented like this, so east-west, one is north-south roughly, and then if you move on another phase, you still recognize another system at least and another here. So at least, you know, you have some cleavages that are repeated in space, but if you think of the orientation of the planes in here, they will be different from the north-south cleavage you have on this face. So that's a critical distinction. On these other minerals, there is no evidence of that. Optical properties of minerals are reflectivity and luster. The reflectivity of a mineral is by definition a ratio of reflected light to incident light. Sometimes we talk about luster, and it can have different really terms. So you have a summary of the terms here, and they will be handy for you to learn, because I might ask you when we have a chat about the minerals how you would interpret the luster of a particular mineral. So you got here an example of non-metallic or metallic luster, and vitreous, adamantine, resinous, and so on. So these are all things that we need to understand really carefully, because they're very helpful to recognize and name your minerals and properly describe them. Transparency of a mineral is its capacity to let the light go through it. And quite often transparency is reflected in being able to see through the mineral. Okay. Some examples here of very nice specimen of uraninite and autunite, I think it is, as well as rhodochrosite. So that's a carbonate, and you can see clearly the cleavages in this pinkish carbonate. And just to sort of reiterate some of the characteristics of carbonates, so you can see clearly one cleavage in here, and I can see also another cleavage there. So cleavage is so important, and here you see these cubes. So the symmetry is another good indication, you know, that you are dealing with a cubic mineral, and in this case autunite. So the color will help as well. Many times uraniferous minerals will have these greenish colors, and they can also be change their color when they are subject to different light sources. So if you use UV light, quite often the minerals will tend to shine, and they manifest different colors. So those are also quite useful for the recognition of specific minerals, such as carbonates, for example. So what is giving the color? It's quite often the presence of impurities, or the substitution with transition elements, and also micro inclusions. So these imperfections also in the crystals will lead to false colors or change colors for the structure, as a function of structure imperfection. Geochemistry of minerals. So some basic rules. So we talked about substitution and polymorphism already. So remember, substitution is the capacity of a mineral to accommodate different cations or anions in its structure, and they have a big impact on some of the physical properties that arise. So substitution in clays, for example, will lead to different mechanical properties, and also other things are the increase, for example, of substitution in clays with water will render them weaker, and more prone to shearing or failure. Polymorphism, it's just the transition in structure and organization of a particular mineral. We made that example of a diamond, so we are reiterating what polymorphism is, and it's just a change of structure depending on temperature and pressure conditions, really. This can take a very long time, but it can be very quick if we use, a very high temperature, for example. So we heat up a crystal, we can re-equilibrate its structure more rapidly with by applying sort of higher temperatures to it. Rock forming minerals, minerals that form a rock can be classified in specific groups. That's very good to know, because often we have to deal with tens of or hundreds of different minerals. So being able to group them according to their chemical composition is quite useful. And so we will see the main groups of minerals when we talk about them. Criteria commonly applied to identify minerals. Again, the morphology, so the structure is key, the color, and the mineral streak. So we didn't talk about streak color. You have to be a bit careful with minerals. Some minerals will have a variety of colors. They don't necessarily crystallize with a single color. You can have, for example, if you take garnet, it can have really a variety of colors, from green to red to pink, like the grossularia variety of garnet, or uvarovites quite often are deep green. So color in this case would be of no value to the identification of the mineral. But what doesn't really change is the streak color, which is quite commonly a mark that is left on the ceramic plate. So if you remember, we look at the different tools that we can use to recognize minerals, and the streak plate is a ceramic plate that is quite hard, and you can use it to evaluate the streak color. Okay, we'll see that in the lab later on. Luster, again, it's essentially how the mineral looks like in normal light conditions. It may be very shiny, looking like glass, so vitreous. It may look like a metal, so metallic. It may be looking like silk, so very silky. And it might have any other sort of luster, for example, resinous luster, which is quite common for minerals such as sphalerite, so a zinc sulfide. Fracture is very useful if you have cleavage, or if you don't have it. So if you have a conchoidal fracturing, it's going to help you with the definition of what mineral you are dealing with. Twinning, we talked about that. It's the symmetry, so growth of crystals or multiple crystals in a reflected form, essentially departing from a twinning plane. That is certainly key. Hardness test, so fingernail, glass, steel, ceramic plate can help you in the definition of the hardness, and it's related, to the Mohs scale as mentioned and discussed earlier. Reaction to acid is key. Other tests could be the estimation of specific gravity. We'll give an example of that during the labs.
and also magnetism, taste, and finally touch. So how you feel the mineral with your fingers, if it's greasy, if it's gritty, or in some cases if it leaves your hand dirty, it will help you define the nature of the mineral, if it's magnetic or non-magnetic, or if it's tasteless, or if it is salty. It should trigger into your mind the idea that it is a ionic compound and it's likely a salt. Okay, so for example, sodium chloride. So now that we have sort of introduced some of the key properties of minerals, we kind of have to explain more complex structures, and we need to introduce the first key family of minerals. And these are the most important because these are the most abundant that are found in the upper crust of our planet. And so the Earth has a crust which is dominated by silicates. Silicates can be forming with essentially sets of tetrahedrons, but these can form different groups. So they can form individual tetrahedrons that are separated in space in island form, and so these are commonly the nesosilicates. And then you have chains or ribbons that can form, and we'll see some examples of those. So you can arrange essentially templates of tetrahedrons together and also mix them with octahedrons to get even more complicated structures. We will see some examples of that later. So silicates are the most abundant on our planet. They represent roughly 30% of the Earth crust. Again, the chemical formula of silicates or alumosilicates, because they can have also aluminium in them, can be very complicated. You have your tetrahedrons and that can form either planar structures or even 3D structures, and these are quite commonly called the tectosilicates. So if you think of feldspar or quartz, they will have a three-dimensional arrangement of tetrahedrons. So it's useful to know that still the template is starting with a single tetrahedron and then repeating that in space multiple times. And of course, this will result in different strength of the material and different optical properties. Quartz is the first mineral that we consider. It's pure silica, so the formula is SiO2. So it's an oxide of silica, and it does have a tetrahedral structure, and you can see that from the elongated shape of these druidal quartz crystals. So you have multiple crystals forming, and they have at the top a pyramid, and then you have this sort of elongated part of the crystal that is forming a pseudo-hexagonal geometry, but in this case the structure is tetrahedral because it forms 90-degree angles between the faces. So as I said, dominantly you will find it in hexagonal faces, so you will be able to count 6 faces on these rock crystals. And yeah, it's commonly in interstitial minerals. It tend to have these well-developed crystals, but it can be also anhedral, which means that it doesn't have a proper shape. So sometimes it will form veins in a rock that essentially follow pre-existing fractures. Most common mineral in the crust,
12% by volume. Distinctive is the absence of cleavage, and it's conchoidal fracture, as already said, and it's quite hard with your 7, and it's classical in terms of density to 2.65. The luster is vitreous because it looks like glass basically, and in fact it does have the same composition, but it's just with a different structure. So we go from glass that is amorphous to tetrahedral geometries that are typical of the rock crystals. The other important minerals are the feldspars. I've mentioned them already. You can see here we are getting much more complicated with the arrangement of the tetrahedrons. So we do have an elongated cell again, and we tend to have sort of larger spaces that form in the arrangement of the tetrahedrons that we lost big cations, and in this case we are looking at potassium feldspar. So potassium feldspar is one of the key igneous minerals, and so the minerals found in igneous rocks, and yeah, this is just an example of a possible substitution. If you look down here, quite often petrologists build these ternary diagrams. We will see plenty of these during the course, and these, contain essentially 3 cations that represents the 3 possible substitutions, and they form hybrid fields, which are called solid solutions. So you can have a solid solution between sodium and calcium with different percentages. So when we have more than 90% of calcium, quite often you're talking about calcium plagioclase. Instead, here you have sodium. We talk about albite. So this is calcium plagioclase will be anorthite, and albite will be the sodium variety. So you can see we are replacing in the chemical formula, which is essentially dominated by octahedrons of aluminum and tetrahedrons of silica. No, actually, sorry, these are all tetrahedrons. So they can be either tetrahedrons of silica or aluminum. And yeah, the idea is that we fill the large spaces with one of these 3. However, be careful, because in some instances you will not be able to form a solid solution, and so we have restricted fields in which we can find, for example, the orthoclase, like in this particular example. So we have continuous and discontinuous solid solutions. I leave you to this set of properties. I think, yeah, one of the key aspects is that the feldspar is quite blocky, and you will be able to recognize 2 or 3 cleavages quite often in the crystals, depending on its composition. Plagioclase will have quite commonly 3 cleavages. Hardness is between 5 and 6, so it's slightly softer if compared to quartz, and the density also vary, but is very similar to quartz, because these are all sort of silicates commonly found in the upper part of the crust. Okay, returning to some of the features of the feldspars, one that is diagnostic of feldspars is certainly the twinning. We have 2 major types of twinning. One is the Karlsbad twinning, which we have exemplified here in this image, and the other is the polysynthetic twinning, which is in image B. So feldspar will look pretty much as vitreous to pearly in terms of luster. You can see that it's more milky,
so the light doesn't really go through the crystals, which are quite commonly, especially for K feldspar, there will be, so potassium feldspar will be pinkish in color. And you can see that we have two images here, one sort of illustrating these twinning planes, which have essentially are distinct by a typical reflection that is different because of the different structure or different growth along this twinning plane of the two distinct phases of the crystal. The same is true on this side. We change slightly the orientation, and you can see how this phase is reflecting much more light. Polysyntactic twinning is usually occurring at a much smaller scale and is a characteristic aspect of plagioclase. So albite will often have this characteristic micro-twinning, which is essentially distinct by the Karlsbad because of the repeated pattern that is observed, like this example here or here. So you have essentially two, rather than having a single plane, you have a minimum of two planes or more. And so this is the example of the Karlsbad, which has only one plane of separation, and also it's more penetrative twinning because the two crystals are essentially meshed together in a more complex pattern. Okay, so that's the real difference, but in both cases recognizing twinning will be helpful for the identification of feldspar. So in this context now we are moving into a set of, or a family of minerals that are a little bit more enriched in iron and magnesium, and these are commonly termed mafic minerals because of that. This is because the mafic stands for dark or black in color, and in fact ferromagnesium silicates tend to be either colored or really dark, and that's one distinctive feature. Another distinctive aspect is certainly their hardness. So they are quite hard, around the 5 to 6 on the Mohs scale, and yeah, I think the darker colors are likely related to the abundance of iron. If we move into the world of olivine, olivine is a nesosilicate because, as you see from its structure here, it does have essentially isolated tetrahedrons that are, silica and oxygen tetrahedrons. So the silica will be at the center of the tetrahedron, and then you have a bunch of cations that holds together the structure of the olivine. So these tetrahedra are not loose, they are essentially bound to the cations that form the entire structure of the mineral and make this mineral particularly hard. In fact, it's very close to quartz with this hardness between 6.7 and 7. You can straight away see the formula here. Most of the cations that are in pink will be magnesium and iron, so it is correct to place olivine in the ferromagnesium silicates group. I think, yeah, for the sake of sort of discussing the varieties of olivine, we can say that we have two main varieties. We have the phyalites and the forsterites, and this is a complete solid solution between magnesium and iron. For the magnesium variety, it tends to be of a nice green color. You can see some examples here of two types of the peridot variety of olivine. and these are produced off volcanoes. So if you find detrital olivine along sand beaches like in the Hawaiian Islands, these are quite often ejected from the calderas of the volcanoes as well, or the main crater of the volcanoes, and other examples of peridot are instead found and were extensively mined by Egyptians. So they're found in Egypt, and they are particularly large, and they have a gemstone quality. The garnet group is somewhat similar, so but the symmetry of the garnet is cubic, so it tends to be more rounded and forms these very characteristic dodecahedrons that are also typical of other minerals such as pyrite, and which we will see down the track really. But yeah, here you see some garnet in muscovite, and this is typically red in color, especially the pyrope variety will be this color, or the almandine, which is the iron-rich variety, will have this characteristic pigeon red color. So other features of this mineral is its complex structure. So we have essentially a combination of tetrahedrons and octahedrons, and that are arranged in a cubic cell, and they are filled by cations, a variety of cations that will also influence the color as discussed. So you tend to have dominantly calcium, magnesium, and iron and manganese rich varieties, such as grossularia, which is the calcium variety, and yes, these minerals tend to have a vitreous luster, pretty much like quartz to adamantine in some cases, like uvaravites can be quite distinctively green and shiny, and in fact they have gemstone quality because of the hardness as well. So very similar to olivine in terms of hardness, so 6.5 or even higher, go up to 7.5, so harder than quartz. Dense mineral, so I haven't mentioned that before, but olivine and garnet, they can crystallize in at deeper levels in the crust, in granulates, for example. So usually deeper levels mean higher pressures, and so you have the need to equilibrate and obtain more compact structures for the garnets, which will lead to relatively high density, so a lot of atoms within a unit cell. Garnet is particularly important for the study of metamorphic rocks. You can see here it's included with other metamorphic minerals such as these muscovites, and also biotite is quite often. So these minerals we haven't been discussed as yet. We'll introduce them later. These are phyllosilicates, commonly found as main constituents of metamorphic rocks. Okay. If we move into the more complex iron and magnesium minerals, we can sort of have multiple tetrahedrons of silica that tend to form either chains or ribbons, and these are the pyroxenes and the amphiboles. So these have more, elongated habits because of the structure, the intrinsic structure that they represent. So if we look at the pyroxenes here, we have, our magnesium and iron, and essentially it's bound to a silica and aluminum set of tetrahedrons and octahedrons, and it's, a three-dimensional structure. The addition is the presence of larger cations, so calcium and sodium quite often will be part of pyroxenes, and yes, they tend to appear pretty much with a dark color, and they form elongated prisms because of the structure. So we have extensive chains of tetrahedrons bound together. The luster is vitreous, pretty much like quartz, but it's not that these crystals are translucent. This is quite rare. In the majority of the cases, they look black, and the light doesn't really go through them that easily. The density is relatively high. They are found dominantly in magmatic rocks, and they will be one of the minerals that are particularly important for the classification of the rocks, because it influences the color of the rock. So the abundance of pyroxene and amphibole will be criteria that are particularly important. So these tend to be really dark in color, although there are exceptions. Amphiboles, even more complex assemblages of sort of planar sets of tetrahedrons assembled in ribbon-like structures with a large site that is surrounded by tetrahedrons. So in this spot you can place quite a bit of things because of its accommodation sites, and some of that are these other hydroxyls. So it's easy to host water essentially within an amphibole, and this is an important property of the amphibole. In particular, varieties such as hornblende will contain significant amounts of large cations that are including water as well as fluorium, for example. So in terms of hardness, they are even softer than pyroxene, but pretty much overlap in this category. But yeah, you will be able to distinguish hornblende in some cases because it's more greenish, dark black. So it will be black to greenish, and has these sort of more complex set of cleavages with different angles that are also a distinctive feature. Otherwise, they're very similar, and they can be easily confused. Distinctive, again, the cleavage, elongated habit in metamorphic rocks, so they tend to be found also in metamorphic rocks like pyroxene, as well as igneous rocks. The ferromagnesium phyllosilicates, so the micas, differ in terms of structure from pyroxene and amphibole, and it's more sort of represented by monoclinic varieties which are distinguished for a characteristic single cleavage, which is commonly a plane of weakness that renders this mineral particularly soft. They tend to have, an hardness that is far less if compared to pyroxene and amphibole. So that's really a diagnostic features of phyllosilicates. We have 2 or 3 main phyllosilicates that we are going to recognize in this course. One is biotite, and another one is chlorite. You have some good examples in these pictures on the right. So that's a classical crystal of biotite, which often has these pseudo-hexagonal shape, and that's quite distinctive. Chlorite instead quite often doesn't really show this type of classical symmetry, it rather has a more massive aspect and form plugs that however have a distinctive greenish color. So chlorite will be quite often greenish, and it's a good indication of metamorphic grade for rocks as well. So here you see a specimen that has also quite a bit of garnet. So some porphyroblasts of garnet are also present in this rock. Okay, I think I discussed some of the key features. So remember, these are minerals that are much softer if compared to pyroxene, amphibole, or quartz. There are also non-ferromagnesium phyllosilicates, and these fall under a common name of muscovites. So muscovite is very similar. You can see here a large muscovite crystal. It does have this pseudo sort of hexagonal shape, and you can see a set of planes here that do represent the classical one cleavage found in these minerals. Similar hardness for that, because this is a plane of weakness. So we tend to have that this is particularly weak, especially if we look at the structure of these minerals, okay? And that's because we tend to have a set of packets that are represented by tetrahedrons and octahedrons that form this TOT, so tetrahedron, octahedron, tetrahedron packages separated by a larger cation, in this case potassium for the muscovite example. If you stick other cations, usually you end up with different clays that will be more elytic, for example, and they will contain things like aluminum, magnesium, iron, silica, and also the OH can be part of the structure of these ylites. So that's pretty much in terms of other features. I think one diagnostic feature for distinguishing between biotite and muscovite is certainly the luster. Luster is more pearly and it's more white to gold in color, with metallic reflection in the muscovite. Usually the muscovite is translucent, so if you remove a small plug of muscovite, so a small foil, it will be totally transparent. Instead, biotite is usually very dark and it doesn't really, light hardly goes through it. So that's another way of recognizing the two minerals depending on the translucency. Other aspects, the strict color can be white or light green. Usually the muscovite is different with the streak if compared to biotite. Biotite tends to have a much darker streak. So that can be helpful, although in some cases it cannot be. So they can be very similar, but sometimes the muscovite will have a white streak, and it's so easy, if that's the case, to distinguish it from biotite. Other more complex phyllosilicates are the serpentine group. These are characteristically represented by magnesium-rich varieties, and these are the chrysolites and talc minerals, which are the softer, because you have even weaker sort of bonds between packages, so you don't have a cation that is holding together the structure in the trioctahedral and dioctahedral variety of these minerals. So we got here the antigorites, chrysolites as an example, and also the talcs. So they have very similar structure, just an increase in the number of silica atoms here, and a different coordination with hydroxyls. Some of the characteristics here, I think it's important to highlight that these minerals look like fibers many times. So you have here a chrysolite vein within a serpentine, and so a serpentinite. So this is serpentinite is the rock, and you have a chrysolite vein which is distinguished by these subvertical fibers, which can be quite soft. So if you touch them with your fingers, you can easily scrape off these different fibers of the chrysolite vein. Usually they are quite waxy, so the feeling is really like touching wax. So it's quite greasy feeling to the touch on your fingers. And if we talk about talc will be number one on the hardness, so it's the softest known mineral, basically. If we complicate things further, we get into the clay worlds. We have two examples here, lizardite and kaolinite, very similar compositions, but for the kaolinite we have more aluminum dominated compositions. So you have an example here of kaolinite. Usually clays are made up of very small particles, so you tend to have very massive rocks in which you cannot really recognize the crystals because they are so tiny. In fact, here you have a SEM image showing the size of the clay flakes. Clay flakes will be, on the order of 10 microns, so very tiny crystals, which, represent some of the key aspects really of the application of clay. Because when you have a clay that has so tiny crystals, it is often indication you have a lot of available surfaces, so clays can be highly reactive and they can incorporate quite a bit of extra cations in their structure. So between these TO packages, so main distinction here is that we are working with TOs, not TOTs, and we have sort of space for incorporation of water, so hydroxides such as OH minus or other things, so other cations that can go into this structure, so they can absorb quite a bit of water. And this is a particular property that is found in a variety of clays called smectites, which can grow significantly. This concept is also represented here quite well with this diagram that shows you the variety of packages, so combination of tetrahedral with octahedral and progressive increasing complexity with the incorporation of additional cations. So you can start with kaolinites that have the characteristic TO package, move into micas, and from there everything is TOT, and what changes is the space between the packages that is increased to a point in which they become unstable. In fact, smectites and vermicolites can grow significantly with incorporation of water, and this is so important for stability analysis. Carbonates are another world. We are moving into things that are no longer silicates.
So the classical examples are the calcite and dolomite, and essentially dolomite is a double carbonate. Things that are distinctive really of calcite are his translucency. So it's very similar to quartz, but has a classic property, optical property, which is called birefringence, and usually the shape is rhomboedral. If you can see euhedral crystals, so well-formed crystals of carbonate will be looking like a rhomb, and they display this classical double refraction. So if you draw a line on a piece of paper and you place a crystal on top of that, you can see that the line is essentially doubled. So this is the effect of birefringence. Any object that is emitting a light or reflecting light will be going through the crystal, and the light gets separated in two phases, and as a consequence of that you can see essentially two images, which is a factor that the depending on the orientation of the phase of light, you get a separation because they have different velocity through the crystal. Dolomite is, slightly different. A key distinguishing factor really is the usage of acid. So if you use chlorhydric acid on calcite, it will be heavily effervescent, so it will react a lot with the acid. Instead, the dolomite will be hardly reacting. In fact, if you want to make it reactive, you will need to warm up and pulverize the dolomite. Usually it's heavier, and often dolomite has some cavities because of the reactions that tend to transform calcite into dolomite, which quite often leads to a reduction of the volume of the crystals. So you will recognize typical cavities in limestone that contain dolomite. These are another important group, and these are represented by two minerals, gypsum and anhydrite. Gypsum is quite soft, so the hardness on the Mohs scale is 2, and that's a diagnostic feature for this mineral. So you will be able to use, for example, a copper coin and scratch easily the surface, or your fingernail will also be able to scratch gypsum. It's quite translucent, so the light will go through it quite easily, so it's a transparent mineral. It does have, in some cases, pearly luster, and its density is relatively high on the 3.32 mark. Anhydrite usually is more granular, so it does have a crystalline aggregation that is quite common. You can see the example here. It's more massive with very tiny crystals. I forgot to mention that in this case you can see a plane of symmetry going through the gypsum, and you form a classical sword-like twinning, which is quite typical of gypsum, and similarly, to what we saw for quartz with the Japanese twins, you can use that as a diagnostic feature for the recognition of gypsum. Anhydrite is also a little bit more greasy, if you want, and if the anhydrite has a proper habit, it will be more tabular or stubby, with prisms forming with the 3 classical orthorhombic cleavages. Phosphates are another important family, like carbonates and sulfates, and the key mineral is certainly the apatite. So you distinguish these minerals because of the phosphate group that is present. They tend to have quite a bit of water in them, as well as other things such as chlorine or even iron in their structure, which is commonly hosted in the center part. So somewhat a structure very similar to amphiboles, with these very large sites where you can host bigger cations and water. And then you have sets of octahedrons in blue, and in pink some tetrahedrons as well, which sort of have the characteristic presence of phosphates. Okay, so you can see these crystals are relatively elongated, and they are quite stubby, and have a basal that surface that is hexagonal, like the muscovite we saw before, or the biotites. The luster is vitreous with a white yellowish color. Somewhat the phosphates tend to be similar in color to feldspar. So you have to be a bit careful in assessing if a rock contains feldspar or phosphate, such as apatite, but quite commonly they don't display the same type of twinning that the feldspar has, and also you do not see feldspar forming pseudo-hexagonal basals like the apatite does. So the difference in the structure, I think, is critical, and the habit of the minerals will be a diagnostic feature for them. Another aspect that is distinctive, I think, is that the cleavage will be poorly developed. Instead, in the feldspars, the cleavage is well developed, and you can recognize it quite easily. Out of interest, the apatite is commonly found associated with uranium deposits, and it often hosts also accessory uranium in its structure because of those large sites. Halides are another interesting family. The halides are the salt, so the kitchen salt. It's clearly recognized by its structure. It's cubic, and you can see an example here of a perfect cubic crystal of halite, and the key distinctive aspect, I think, is that it has a salty taste. So that's a quite common way of distinguishing halite from fluorite, which we will see, which is still can appear as a cubic mineral and has similar translucency. So table salt, vitreous luster with the perfect cubic cleavage. So we will see at least 3 cleavages, and yeah, the salt is usually related to marine processes. So evaporation of water on flatlands can lead to accumulations of salts of a variable composition, and some of them will be NaCl. Other salts could be potassium salts, for example, mirabilite, or other type of compounds such as sulfates will tend to form in this environment. And this is the example we saw of gypsum and anhydrite. So yes, in summary, in conclusion, we can say that it tends to form in restricted basins through evaporation processes of seawater, involving seawater. Fluorite is rather a calcium fluoride, so double fluoride in this case. It's still cubic, so in this particular case we have cubes that are pinkish in color, and we have sort of a set of these crystals that are attached to the classical druidal quartz or smoky quartz in this particular example, but you know, it's still that rock quartz that we saw before with a slightly more smoky color, which is more brownish but still translucent. So quartz is this one, and you can see this pyramid on top of the prism of quartz, and here you can see the edges at 90 degrees of the cubes of fluorite, and this is pinkish, very beautiful fluorite. Quite often fluorite will have a different color. It is more greenish, and it gives you the feeling of looking through seawater, which is a quite diagnostic feature of fluorite crystals. Fluorite can be also anhedral, so it does come in different forms, and that can be also a challenge for its identification. Fluorite has an hardness of 4 and a relatively high density considering the average crustal density, so which is 2.7, so slightly higher than that on the 3.2. Industrial applications of fluorite are extensive, but certainly the hydrofluoric acid production is key. And often we have different varieties of fluorite, so we can have hydrothermal fluorite as well as fluorite forming in sedimentary environments in association with limestones. So a variety really of environments of formation. Here on the image you see an association of quartz and fluorite that is hydrothermal. Okay, we are left with what are called or termed opaque minerals. So these are two families, the sulfides and oxides. So we are going to review very briefly some of the sulfides now, and later we'll discuss the iron oxides. So here we are focusing really on iron related minerals, so we will review mostly the iron sulfides as well, but these are, you know, metal compounds that can have a variety of transition metals included in them. So we have copper, zinc, lead, silver, and also other sort of base metals and precious metals that are involved in sulfides. For example, gold can be commonly hosted within pyrite, which is the key iron sulfide. We'll see that later. Yeah, but remember, these are very stable compounds, especially in reducing environments. They are relatively rare minerals, and this is because they're composed of trace metals, so they represent roughly 0.15% of the Earth's crust, but they are particularly important because of the fact of including base metals and precious metals, so they are extremely important for transporting essentially these metals and concentrating these metals in our deposits. So this is why it's good to know about sulfides. So if we look at the iron sulfide, it's the fool's gold. So this is, of course, because of its appearance, it's
characteristic for its metallic luster, but it does have this gold-like appearance that render it very easy to recognize in any specimen. It's a cubic mineral, so you can see up here the structure of this iron sulfide with a coordination that takes two large anions of sulfur and combine those with one iron. On this image you see a classical dodecahedron of pyrote, but we can have also other configurations that represent more easily the cubic symmetry. So cubic pyrote is in here. Often pyrote is quite hard, so we have an hardness of 6 to 6.5. These other case in which we call it a replacive process. So we do a replacement of organic matter, in this case, which could have been aragonite or calcite in this particular fossil, which is called an ammonite. So ammonites often during diagenesis and during the process of lithification, we tend to substitute some of the organic matter and replace it with a process called pyritization. And so pyritization will lead to the replacement and mimic the shape of the organism that is replaced. Oxides and hydroxides represent the last important group of minerals that we find in the upper crust. You have to keep in mind that oxygen is a key element for our planet. Roughly half of our planet considers oxygen, or is made up of oxygen in different compounds. We saw the silicates, they contain oxygen. We saw other key minerals such as phosphates that contain oxygen, and now we see oxides which are devoid of silica and are essentially compounds that consider transition metals with oxygen. In this case we focus on the iron variety of oxides, which are the magnetite, hematite series. So if we move to the first, hematite is essentially an iron oxide, and you can see a coordination of 3 atoms of oxygen with 2 of iron. This is well represented here in the structure of hematite, which is rhomboedral. So you can count the 3 atoms of oxygen in coordination with the iron. Okay. The structure of the hematite macroscopically can be massive, or she can be recognized by these characteristic laminae, which is also an indication of its growth. So the ingrowth of crystals often looks like a rose, and it's quite characteristic. Also, you can see this is an opaque mineral. It does have submetallic to metallic luster, and that's diagnostic as well, but you can confuse it with magnetite, which is this cubic variety of iron oxide. But yeah, distinctive is the streak. So a blood red streak will be a way of differentiating. So you can recognize the difference by using the streak plate. The high density is also an important distinction which works also for distinguishing sulfides and oxides from silicates, and also the hardness. I think it's it's important to know, so between 5.5 and 6.5. The importance of hematite is with respect to its exploitation, because of course iron is used for the steel production, and yeah, we have incredible accumulation of iron ores in Pilbara that are dominantly hematitic. These ores are part of the Western Australian Pilbara Craton. So one example could be the Armersley Basin. In this area you find important accumulations of hematite, and so this deposit will contain on the order of 60 to 70% hematite, which is commonly found in microplatyform. So Australia has been historically a critical continent for the exploitation of iron ore, and I think after the embargo for the export of iron in the 60s was lifted, most of the deals that today occur between China and Australia are really driven by this economy. We are left with magnetite, which is the last oxide that we review in this first lecture. Magnetite will be a more reduced oxide. The fact that you can see in this image an octaedral crystal of magnetite, it's a good indication that you are dealing with a cubic system because of the symmetry, and you can see the color. It's pretty much gray and with the clear metallic to submetallic luster, very similar in a way to hematite, with this very rusty appearance. It's a little bit harder if compared to hematite, and distinctive is the fact that this is a magnetic mineral. So magnetic minerals will attract or be attracted to a magnet. And also the streak is black, so that's also a distinctive feature. It's useful in geology because some of the geological studies really focus on reconstructing the dynamic and movement of continents, and so paleomagnetic science has been possible thanks to the existence of magnetite. In these final slides I provide you with some basic information about the classification workflow, and we discuss how you should describe the characteristic of the minerals that we just reviewed. So I think it's valuable to consider a chart of this type. You can see here essentially a workflow that you can adopt to make decisions progressively and evaluate what is likely the mineral you're dealing with. We'll make a quick example. If I start and I can recognize that the mineral has a platy habit, so it's composed of laminae, I would have to start to question, for example, the color. So if it's a black mineral or very brown mineral, if that's a yes, then it's likely to be biotite. Instead, if the answer is no and the color is silvery white, let's say, then it would be more likely muscovite. So this can be applied to a number of minerals, and you can use it as a guide for the classification of minerals. So this has to be a process that is quite systematic. So I provide here a way of sort of labeling your minerals and describing them as a summary. And so you will have to sort of report any code that is available on the mineral, quite commonly, then describe the color, the luster, the cleavage, hardness, streak, and all these other properties that we already extensively discussed, and at the end give a name to the mineral. So some of the assignments that are part of this course will consider the discussion and description of minerals. This will be based on a set of videos or images that will be made available to you, since this is a course that is run dominantly on an online form. In this case, I provide also a final slide here with a summary of the minerals that are object of examination in this first part of the course. And so when you do your oral examination, it is likely that we will discuss some of these minerals, so you better consider them and sort of learn their characteristics. There is a book that I recommend in the syllabus, which is a book titled An Introduction to the Rock Forming Minerals. And I strongly advise to consider the descriptions of these minerals that are present in that book. And this concludes our first lecture. And if you have any questions, you feel free to email me or contact me, and I'm happy to discuss any aspect that concern the content of this lecture. In the next lecture, we are going to look at more global tectonic processes, and we'll start to look at our planet more in detail, so that we can place the minerals in the context of rocks and start to discuss the different environments of formation of minerals and rocks. So I think we'll catch up in the next lecture for further discussion. Thank you.